All right, we're continuing with Chapter 8 in the statistics textbook. In this video, we're going to go through the fourth section, which is on computing the correlation coefficient. All right. Here is the procedure for computing the correlation coefficient. Convert each variable to standard units. The average of the products gives the correlation coefficient. So this is really interesting. If you Googled how to compute the correlation coefficient between two variables, what you'll typically see is this formula here, which they show this at the end of this section. It says there's another way to compute R, which is sometimes useful. You do the covariance of the two variables divided by the standard deviation of X times the standard deviation of Y, where this is the covariance. Okay, but I think this description here is really useful because it can help us with our intuition behind what exactly the correlation coefficient is. And then also, I think this is a lot easier to remember as well. Just convert all the data points to standard units and then take the average of the products of those standard units. And then, from that standpoint, since in general situations, we'll be dealing with more than two variables, it makes you wonder, well, what if we had three variables? What if we converted three lists of data points all to standard units and found the average of the products of each of the three corresponding data points? What would that mean? And so at the moment, let's just think about it. If we had more than two variables, if we had, say, X, Y, and Z, then what we could do is compute the correlation coefficient between X and Y, between Y and Z, and between X and Z. And then we'd have these three correlation coefficients that we could then compare. Now, you might have been wondering, as we've gone through this chapter, does it matter if we look at, X versus Z or Z versus X? Well, okay, so we started off by talking about the scatter plot. And from the standpoint of the scatter plot, it would matter in the sense that if you had something like this with X and Y, and then you flipped it to Y then X, then it would just like mirror flip all the data points about Y, the line Y equals X. If you remember from algebra, when that's like an inverse. If you have X and Y and you take the inverse, then you flip the data points, all you're doing is just flipping the graph about the line Y is equal to X. So these data points would do this. Okay. Now, so we talked about the scatter plot, but then in section 2, we went straight into the correlation coefficient. Okay. So now in relation to the correlation coefficient, what we can see is that you convert the variables to standard units and take the average of the products. So you have the list of X variables, the list of Y variables, and then you convert them to standard units, X standard, Y standard, and then just take you multiply. So you just create a list here of XS times YS. Multiply the first two, second two, third two, then take the average of these. Well, that has no dependence on the order. So there's not like any correlation coefficient when it comes to like the correlation coefficient of X versus Y is going to be different from the correlation coefficient of Y versus X. The correlation coefficient between two variables is the correlation coefficient regardless of order, right? Because again, you're just taking it doesn't matter that if you look at this definition of how to calculate the correlation coefficient, same here. Well, we have to look at what the covariance is. Okay, it's hard to see here, but from this definition, it's clear that the order doesn't matter. There's no X versus Y correlation coefficient and then a separate Y versus X. Okay, so we know how to convert to standard units. That's just the number of, you find the standard deviation of an entire data set, and then you just, the standard units is just the number of standard deviations that a number is from the mean. So, okay. Standard units were discussed a few chapters ago. This procedure can be given as a formula where X stands for the first variable, Y for the second variable, and R for the correlation coefficient. So average of X in standard units times Y in standard units. Yep. So if we, let me take this background off. Okay. So if we do that here for this data, then what they're saying is we need to get the average and standard deviation of the x variables, and then use that average and the standard deviation of the x variables to convert these variables to standard units. Then come here, get the average and standard deviation of the y variables, and then convert the y variables to standard units. So then we'll have this new table, x standard units, y standard units. Then we can create another just single column. It's not two rows of x times y, x times, or xs times ys, xs times ys, xs times ys. And then just get the average of this. And that's the correlation coefficient. So let's see. Yes, they're just mentioning here that the pairing matters. That's, yeah, when it comes to relations between variables, the pairing absolutely matters, right? If this was like father's height and son's height, you can't just randomly mix these up. And so, yeah, you couldn't, the correlation coefficient is going to be incorrect if you start multiplying numbers, x's and y's, standard units that aren't paired. Okay. So step one, convert the x values to standard units. This is quite a lot of work. You have to find the average and standard deviation. Exactly. So here's the average of the x values. This is 1 plus 3 plus 4 plus 5 plus 7 divided by 5. So 12, 16, 19, 20. 20 divided by 5 is 4. Standard deviation is 2. Then you just go to each data point and see how far it is from the mean. 1 minus 4, this is going to be in the negative direction, divided by 2. It's minus 1.5 standard deviations. 1 is minus 1.5 standard deviations from the mean. Now you've got this new, these are the XS's, the 5 XS's. Okay? And then they do the same thing with Y, and now here's the products. And they're going to, so these aren't, we're not squaring anything here, so you could have some of these products be negative. And then you just take the average here, and that's the correlation coefficient. And that's what they do here. And so the correlation coefficient is positive 0.40. Okay, so this completes the solution. If you plot a scatter diagram for the data, the points slope up but are only loosely clustered. Yeah, so 0.40, it's an upward slope. But if we look here, here's the points. They slope up, but they're not. It's a loose clustering, right? If we think about a line, something like this, I guess that maybe would be the SD line. Then it's like a loose clustering, right? These are clustered pretty nicely, but this one's way off. And since there's only 4 data points, this can really pull down the correlation coefficient. Okay, so now why does R work as a measure of association? In figure 9a, the products are marked at the corresponding dots. So here's the products. The products of the standard units corresponding to each data point. So this is the data point 5, 1, or 1, 5, but its product of the standard unit of standard units was 0.75. Okay, so it says, now horizontal and vertical lines are drawn through the point of averages, dividing the scatter diagram into 4 quadrants. Okay, these horizontal and vertical lines drawn through the point of averages. If a point is in the lower left quadrant, both variables are below average and are negative in standard units. So the lower left quadrant means both of the products are, or both of the variables in standard units are positive and below average. So, okay, again, both standard units for X and Y are positive, or no, wait, no. Both, in this quadrant, both variables are below average and both are negative in standard units. So the product comes out positive. Here, both variables are above average and in standard units, both are positive. And then here you're going to have some alternation between the standard units are positive or negative, and this is both variables are above average, both variables are below average. It's the same idea here with the quadrants. Here they're saying this is a positive correlation coefficient, this is a negative correlation coefficient. And what you can see is that when you're taking the average of the products of the standard units for a high correlation, you want to have matching positives or matching negatives for a high magnitude correlation. You don't want a mixture of negatives, negatives, and positives, because then everything cancels out. And so that's how it works. It says if R is positive, then points in the two positive quadrants will predominate. If R is negative, points in the two negative quadrants will predominate. Okay, now let's work these exercises. It says, this first problem says, for each of the data sets shown below, calculate the correlation coefficient. Okay, so each of these data sets, let's come to Excel. All right, so let's get the average of each of these. Okay. All right, now the standard deviation. Okay, so I can just... So same average and same standard deviation. Huh. Okay, now converting these to standard units, you've got, so take the data point minus the average divided by the standard deviation and fix that. Okay, no, I need to fix this as well. Okay. Okay, now copy. All right, now do the same thing here. You've got the data point minus the average divided by the standard deviation. Okay. All right. Now we need to do the product of the standard units, the sum of the products. So okay. Oh, but then take the average of that. So take all of this and divide it by 7. Okay. Okay, and I actually need to change this. The standard deviation should be the population standard deviation. It's slightly different. We'll learn about the difference between the sample and population standard deviation later. So let me change this. Okay, so there's the correlation coefficients. Minus 0.93, 0.82, minus 1. Which is kind of interesting because they all have the same average and same standard deviation. Both X's and Y's in each of these data sets have the same average and same standard deviation. Interesting. Okay, find the scatter diagram in figure 6 on page 127 with a correlation of 0.95. Okay, there it is. In this diagram, the percentage of points where both variables are simultaneously above average is around. Okay, so the point of averages looks to be somewhere around here. And so we can draw a horizontal and vertical line going through this point. Okay, so simultaneously both being above average would be over here. To have both the y be above average and the x. So the percentage of the points where both are above average is about 50%. Okay, repeat exercise 2 for the correlation of 0.00. Okay, so the point of averages looks to be about right in here. Okay, so in this case, it's like 25%. Interesting. Using figure 7, repeat exercise 2 for a correlation of minus 0.95. Okay, so we're going to have, let's see, we're about right in here. So in this case, 0%, okay, but the 5% is correct. I probably don't have the point of averages exactly correct here. 5%. Interesting.